Hey, all right, class. Let me start another video solution here. And so let's look at number 19, particularly part B, but let's kind of work through it starting with A. And so I'll read it. So it's from chapter 18, number 19. It says here, in the arrangement shown in the figure, an object can be hung from the string. And then it goes on in parentheses. The string has a linear mass density of 0.00200. Okay. That passes over a light pulley. So it looks something like this. There's a little oscillator here. Let me just kind of label it with some kind of up and down motion. And then the string extends across and goes over a pulley. And hopefully you kind of recognize it because this is the same kind of apparatus we did for the lab on the string waves. And the oscillator would go up and down, and in our experiment, the oscillator was set at 60 hertz, and, can't change that. In fact, ultimately, this is going to be the question of part A, what is that frequency? But it would look maybe something like this, and so here was the point I was trying to make in the lab, as well as the author was here in the book, that you would get a wave pattern that would go down and bounce off, and so you would get some standing waves. Now, I would be a little careful about calling the oscillator a node because the oscillator does move a little bit. Now, if the amount that the oscillator moves is small compared to the amplitude, so if we get a really good, strong resonance, we could say that this endpoint here where the oscillator is approximately a node. But the ones that aren't moving, and they stand out with our eyes, would definitely be nodes, and this is what I did in class. And the top of the pulley would definitely be pinned down because of the tension of this hanging mass M would be a node. And so in the lab, I measured from here, and if I had enough room, I would go all the way to there to get a full wavelength. But if it was so long I couldn't quite get it, then I would just measure to this one and then double it. But I never did I come over here and call that a node, because the only way you can really kind of justify it as a node is to say it's approximately a node. And the bigger the amplitude is compared to that, the more that is true. And so you really got to tune these up really carefully. And I didn't, want to do that during the lab and take the time. And it's just not necessary for what we were doing. But for this problem, if you look at the picture, they're trying to show you that you can treat this as a node. And they should be more clear because it really is not a node, but it is close to being a node. And the bigger the amplitude is compared to the amount of vibration, the closer it is to being a node. Now, in our setup in the lab, this amplitude was maybe about 1.5 times that one, so that really didn't justify it. So in the lab, if I would have called that a node, I would have gotten some pretty poor data. But in this one, in the picture they're trying to show, I think it's okay to call that a node. In fact, that's the only way you could really kind of solve it, is if you assume it's a node. So then they also give you this whole length as 2 meters. Let me just call it capital L for the length of the string. Well, in fact, I should keep reading because that's what they say here. Okay, so passes over a light pulley. The next sentence says, the string is connected to a vibrator that vibrates at a constant frequency, and the length of the string between point P and the pulley is 2 meters. So there's the 2 meters. It says, now, when a mass M of an object is either 16 or 25, standing waves are observed, but no standing waves are observed with any mass in between that. So what they're saying here is you wouldn't get a real big amplitude unless you hang M equaling to 16 kilograms or M equaling 25 kilograms. It's just, not the same value. Okay. So one thing to keep in mind here, and maybe I should write it this way, and it looks like the author goes on to give us a little hint, but if you go to do the wavelength, which is velocity over frequency, and I'll just write 1 over frequency, and the velocity is the square root of tension over the mass density. In fact, maybe one more step here. The tension, then, is the mass that's hanging. You can kind of see here that this is saying that the more tension you get, the longer the wavelength is. So if this is the picture, and I don't know what the right picture is. I drew 3 humps because I was lazy, and I'm looking at the author drew 6. But whether it's 3 or 6 or some other number that we have yet to solve for, I just know that if you were to add more mass, and so maybe if you let this picture represent, when I'm hanging 16, then if I were to draw another picture, so maybe here's the oscillator, here's a level string with no vibrations. Now let me hang the larger of the two, the 25. This more tension would result in more wavelength, or a bigger wavelength. And so it would look maybe with 2 humps in it. That's a terrible drawing. Forgive the drawing, but it's the idea. And the tension has to be just right, so the wavelength gets to be just right so that this is a node. And that's what they mean by a standing wave pattern. Okay? So, if you were to hang something between, like 20, you wouldn't get anything because this wouldn't be a real node. It would just be kind of wishy-washy, and the amplitude wouldn't be very big, which is why, I didn't want to mess with that during the lab. Okay, so knowing that, then, we can continue on and write something like this. But I better get to the question. So the question says, A, what is the frequency of the vibrator? And then this is the hint that I kind of already went over. It says the greater the tension of the string, the smaller the number of nodes. See, so the greater the tension, the greater the wavelength, which means there would be less humps, less nodes. So keep that in mind as we work on this. Because if I were to write it a little different, so if I were to write frequency equals velocity over wavelength, then that's what I'm looking for. I'm looking for that frequency right there. And it's consistent. So let me do this. Let me put the 1 over wavelength alone and then put the velocity as mg over mu. Okay, so there's the tension involved. Okay, now, the other thing to keep in mind here, and you can kind of see this in this picture, or some of the ones we did in lab, or your author's picture, this we would call the third harmonic, because there's, 3 humps. This we would call the second harmonic. But in general, if we let n be the number of humps, and so the harmonic, n half wavelengths is the length of the string. So we could rearrange this to say the wavelength is 2L over N, and we could put that into here. All right, so putting the wavelength, that would be a 2L, and then flip it, that'd get an N, and that would get the square root of mg over mu, and that would be the frequency. Okay? So if I were to maybe apply this equation to the one with the fewest harmonics, so the 25. Again, I don't know, I drew a picture of 2, but I don't know it's that. I would get something like this. The frequency equals n, so the number of harmonics, which I'll just kind of mentally picture 2 for a moment, over 2L. Now, L is 2 meters, so I'm going to put a 4. Over the square root of, and this would be 25 times g over mu. Then, this has got to be the solution. Oh, maybe I should have put in mu. Ng. Well, I know those. And I guess what I'm trying to say is right now I have an equation that there are 2 things I don't know. I don't know how many humps there are. I don't know what harmonic this is, and I don't know what the frequency is. But if I do that same thing for the other equation, of course, then I have 2 equations with 2 unknowns. So let me apply this same equation to the 16. So let me go ahead and say F equals. And now it would be one more harmonic. They made that very clear. There was nothing in between. So this would be n plus 1. So however many harmonics I had when I was 25, I'm going to have one more when I hang 16. And so, again, I have two unknowns. And so these two equations, I can set equal to them. They're each equal to the frequency. So now it becomes just a little math game here. So I'll put this first one, so n over 4 times the square root of 25g over mu. So that right there equals the F. But that also equals to n plus 1 over 4 times the square root of 16g over mu. Let me switch over to a new page. So page 2 here. And say, all right, let's take that equation. And, of course, the 4's would cancel off, and the square roots of g would cancel off. The square roots of mu would cancel off. And so I would get an n times, and the square root of 25 is 5, would equal then to n plus 1, and the square root of 16 is a 4. Let me write that as 5n. Let me do the distributive property, 4n plus 4. Move or subtract a 4n, and I get n equals to 4. So n plus 1 is 5. So my drawing here for the 25 should really look like this. 4 little humps, 4 half wavelengths. And so n equals 4. So my drawing for the 16 should have 5. 1, 2, 3, 4, 5. So this is really what the drawing should look like. I'll write it as n plus 1 equals 5. So 5 half wavelengths fit in here, and 4 half wavelengths fit in there. That's what this is telling me. And of course now I can come back to either one of these two equations, now that I know what n is, and put it into either one and solve for f. And they, of course, should come out to be the same thing. So I'll just take that first equation here on page 1. So f equals, and so I'll have n equal to 4 over a 4 times the square root of 25. G is 9.8, and the mass density is 0.002. And now I can get the frequency. Actually, the 4 cancels off, so I'll leave that alone. And I'll just go, okay, the square root of, and it'll be 25 times 9.8 divided by 0.002, and looks like 350. So 350 hertz is the answer to A. What is this frequency? All right, so let's go on to the harder one, B. Maybe it's not harder, but conceptually, it's got a little subtlety in here. And that may not be so obvious. Because it says, what is the... Oh, and I got to go to the next page. I'm reading the textbook, not the PDF I sent you guys. But what is the largest mass of which the standing waves can be observed? Okay, well, let's come back to this picture, because now that we see that hanging 16 would make 5 hums, the fifth harmonic, and hanging 25 would make 4 hums. Hanging more mass would make 3, more mass would make 2, more mass would make 1, and if you go more than that, you're really not going to get oscillations. You're really not going to get a standing wave pattern. You would just get something that would, be from the top of the pulley to the movement of the oscillator, and the wavelength would be something. But to get a really nice oscillation, you want this oscillator to be approximately a node, and your amplitude really high then. And that would only occur if your oscillator is near a node. And so longer wavelength, that is more tension, won't allow for that. So that's probably the hardest part of B, is conceptually understanding that there is then a maximum tension corresponding with this wavelength, that is this being a node, because if you go more mass, you get a greater wavelength, and you don't really get a strong oscillations. You get something that is kind of boring. You get a node where it's tied down, and you get an amplitude that's just the movement of the oscillator. And that's not quite what we want. Okay, so this really is the key. Because if we come back to that equation, here it is right now. And so we say F equals, and this would be the number of half wavelength, that is the harmonic mode, square root. And let me write this as M 9.8 and mu is 0.002. What I can do now is I know this frequency. So this is 350. And conceptually, coming back to this, I know that we're talking about making this whole thing right here the one hump. And so n equals 1. Okay, so 1. And then what mass is needed to do that? And then solve for that mass. Okay, so I'm going to get out my calculator here, go 350 times 4, first of all, move that over. Then I'll square that, so I get all this good stuff here under the square root. Multiply that by 0.002, divide that by 9.8, and the mass comes out to be 400 kilograms. So the 400 kilograms would be the most. All right. That's got an interesting set of physics. You gotta figure out the n from the picture, from the physics. There is no mathematics. You got to get that 1 out of there. So hopefully that all made sense, and I will talk to you later.